I am Shlomo Havlin from Israel, and I will speak to you about a phenomena which I call spreading phenomena, which occur in many places. And let me show you my talk. It's here, yeah. Okay. Okay, now spreading phenomena. And specifically, I will speak about several spreading phenomena, in particular epidemic spreading, that we have the pandemic, the COVID-19. And I will speak on a work also that we do together with Tokyo Institute of Technology. It is fake news. I will start with the fake news. And the point that I want to mention here and to emphasize that how to use network, for example, to distinguish between real and fake news. And as you see here, the work is in collaboration with Professor Misako Takayasu group in Tokyo Institute of Technology. I point here several papers that several of them were published. One of them, the last one is on emotion, on fake news, and evolution of companies, which is also kind of spreading, and also collective human flow in urban area, which is going to be published soon. So the first topic that I want to speak, I will focus on fake news and epidemics, and the rest I will only mention. So when we look here on the fake and real news spreading, and I want to use network to distinguish between them. Why is it important? It's important to know in advance as much as possible if the news is real or fake. And one way to do it is to look on the data and on the language, on the words, on the text, and to analyze it, and then to say, okay, what is fake and what is real? But this takes a lot of time. A lot of people have to look into it, or to use the method NLP. What I'm suggesting here, and this work was done together with Misako Takayasu in her group in Tokyo, is that to look on the network, we can already identify about 80% of the network, of the fake news, and we need only to consider only some of the networks more carefully. So typically what we find is that when we look on the network of real news, it looks like in the right, there is an origin, and many people listen to this origin. Rarely, there is another one that spread it. However, in fake news, because people like to, they are exciting by fake news, they are exciting by news that are really something excited, more excited usually than. So many people start to make their own group. And as you see here, there is one group here, another group here, another group here. So it spreads by groups of people, by clustering of people that are interested in the fake news. But if we analyze the network structure in the right and the left, we can see in many cases that they are very different. And how to do it? We can see here the layers. It means we see as a function of time, how many people were in the first layer, they listen to the first time that the person make the fake news, and how many people listen in the second layer, they listen to somebody that listened. This is the gray color. So we call it layer 1, layer 2, layer 3, layer 4, layer 5. It's layers by layers. The first one is here, and you see here it's about 450 people listen, but there are 200 people that listen to the second one, and about 300 that listen to the third one. In contrast, this is typical. I'm not saying all of them are like this, but more common is like this. And if you look on real news, usually you don't have many layers, you have only few layers, and usually the first layer, the first person that gives the good news, he attracts many people, but not even less people usually than the fake news, unfortunately. This is for Weibo, which was done in China, and the same was done in Japan, in Tokyo, on also distinguishing between fake. You see a fake has many layers, and in the real, you have usually one layer also. So we look on this, and this was published, this paper was published in APJ Data Science, and we analyze this layer. So what we can say that even if we look on 5 hours, this is, we look after 5 hours, here, you can see here, after 5 hours, you can see already the pattern of the difference. Here we see after 5 hours, see several layers. However, here in 5 hours, you see only 1 or 2 or 3 layers, not more. So identification are based on structure after 5 hours is 0.78. It means 78% of the news, of the messages, of the network, we can identify either if they are fake or real. So, but in order to do it automatically, not to look on the network, we define a measure that we call heterogeneity of the network. Heterogeneity of the network means the following. You can define the average degree of a node, which is defined here. You take the sum over ki and divide it by the number of nodes. And the second moment is k squared. It's a very simple measure, 1 over n sum over k squared. And the heterogeneity is calculated as follows. You take the square root of this divided by the average. Now, if the square root of this divided by the average is large, it means there is heterogeneity. It's more like the real news. But if it's small, because here it's less heterogeneity, because here it's much more heterogeneity, there is nodes that have many links and many nodes that have only one link. But here you have less heterogeneity, and we want to see how can we, by measuring heterogeneity, can we distinguish between fake and, because this is very easy to follow. You don't need to know the text, you don't need to read the message, and to identify if it's real or false, if it's true or false. And here we took many messages, many networks, and you can see that usually the heterogeneity is high for the real one. This is the blue. Origin is about. Now the theory tells you that if it's only one person, it should be this number. It goes like n to the 0.5. N is the number of nodes in the network. Of course, the heterogeneity increases with n. But you see here that well separated are the one which are real. Sometimes it's not. For example, this one and this one is close to real, but they are really fake. So there is a way to see if we can distinguish between real and then we analyze it also mathematically to see if we can distinguish between real and fake news and how much we can distinguish. So we look on the distribution of the heterogeneity, how far they are from the full, the H measure tells you how far is this number from the full heterogeneity. This is the line, and this difference is how far it is. And we can see that fake news have usually high H heterogeneity. They have high H, and the real news, they have low H. They are more heterogeneous. And you can see it after 5 hours, and you can see it also for all the data. And when we do it, we can see that we can identify what is real and what is new and what is fake just by looking on this curve. And we can see that, for example, if we want to identify 75% of the fake news, we have a probability 0.79, 0.75. The probability is to identify them. So by this way, we can say, because the distribution of fake news are very different from the distribution of real news, we can identify after 6 hours, 76% of the fake news. So it means we have a probability of about 0.76%, 7.76 to identify fake news, or if we wait at the end, we can do 0.79. So we see that 5 hours is almost like the end of the story. So in this way, together, if we take this together with machine learning, with NLP, we can increase the identification automatically, and probably because we can add to it the NLP, then machine learning, language learning, and then we can identify much better what is fake and what is real, maybe even after 1 or 2 hours, and then to advertise it in order that people will not will not have some damage. So now I go to the second topic, which is also spreading. This is spreading of in social network of news or fake news. Here I speak about spreading of sorry again. Here I speak about spreading of pandemics. The current pandemics, the COVID-19, is very important. And I want to show you how different was the results in China compared to Italy or other countries. So when we look on, I look only on the 2-3 months in the beginning of the pandemic. And what we see in the right, we see how the number of infected people increases in China. In January, they started to count in January, in the end of January, and then in February, and you see how it increases, and then in March, it's already stopped. While in other locations, when the beginning was here, you see it increases, and we have many more cases. And when we look carefully on the rate of the infection, we could see how the rate decreases in China very fast. It means that that in China, in most of the cities, they succeeded to decrease the rate by controlling, by putting the people in isolation, and then it decreases very fast. And very fast, I mean, you can see the numbers here. In Shanghai, it was 13 days. This is a log linear plot, and the decay is exponentially. It decayed exponentially with a time constant of about 10, 13, 14, or 11 days. You can see it also in other cities in China. So first, you can see it was spread, and then after it spread some time, they realized the spreading, and then they control it by quarantine, by closing the people, and then the rate was very fast, and the decay was very fast compared to Italy. While here the slope is 1/14 days, 14 days. In Italy, it was about 50 days. And this, I think, is the difference between not only Italy and China, but also other countries. So the main issue was to control it as fast as possible, and that's how the Chinese overcame the spreading of the disease. Let me show you some more results. We can show that actually the cause of the China spreading was traveling of people from Hubei, from the place where it started to spread, to other places. And here we analyzed several quantities, like the infection of the function of distance, and the infection of the number of people in the city, or the infection about the ratio between the distance and the number of people. What we find is an interesting relation that the infection is related to distance and the number of people of the city to the power minus gamma, where gamma is about 1.85 or something like this. It means that you can see the spreading in terms of how it spread in China from Hubei. Everything that we measure here was from the center, from Hubei. And it looks like a nice power law that can be explained by this function that you see here. More than that, if you look on the population migration of people during the epidemic, because when Hubei started to be an epidemic, there were still buses and trains and flights available. And we could see how many people move from one city to another. And you can see the more people move to a city, the more infected are the people in the city, and it's also almost linear. This proves, at least supports very strongly, that what came out in other cities, each point here is a city in China. And you can see here that the population migration from Hubei number of people that travel from Hubei to other cities, it's proportional to the number of infection of the city. This is a, I think, interesting result that shows actually that traveling brought the infection to other places. And this is how the population migration with distance. Note that population migration with distance is a higher exponent compared to the population, to the infection. And this because there were some restrictions, but they were not enough. This is just the population migration. And this is different from this because there was some restriction, but the restriction were not enough. And that's why the infection was smaller than the real normal population migration between cities. So let me go now now the question is how to solve the pandemics. How can we better quarantine the people or immunize the people, which people to choose in order to immunize and to stop the epidemics in the system. So what we suggested recently in a paper that is now in archive, I hope this is the right one, yeah, a young one, is the following. Of course, everyone knows now that in order to stop epidemics, you need to identify the super spreaders. Super spreaders are people that are infected, but they meet many people. Meet many people, and that's why if you immunize them or you quarantine them, you can reduce the epidemics very fast and very little amount of immunization units. So, but the problem is how to find the super spreaders. You don't know the network of people. You don't know how many people each one meet. You don't know the information. So you cannot identify easily. What we show here in this paper is that you don't need to look for the whole structure of the paper. You need to take several people, maybe 10 people, and choose from these 10 people the best one. Here, for example, I choose 3 people, and I look from these 3 people who is the best to immunize. It means this one, you see, have 4 neighbors. This one has only 3. This one has only 1 only 2. So I choose this one to immunize. What happens if I do it many times, but not knowing the whole structure of the paper? I don't know how to find the super spreader. I find the super spreader from a small group. And what we show here, that if I find the real super spreaders, I need, let's say, I need about 35% to kill the epidemics. This is how what is the size of the epidemics as a function of the number of people that I immunize. So if I immunize 35%, I destroy, I stop the epidemics. However, imagine now that I don't know the super spreader. This is N targeted means to find the super spreader. Imagine that I don't know the super spreaders, but I know only let's say 5 people. I take 5 people, and from these 5, I choose the best to immunize. You see already the 5 gives me a better, almost like not so far from the full knowledge of the people. It means that I don't need to have full knowledge of people, even if I have limited knowledge. And this is how the distance from the one changes. You see, for example, if I know only, I know only 1 people, I need 80. This is 1 minus PC means how many percentage? So 20%. If I immunize 80%, then I destroy the epidemics. However, if I know 10 people, you see, that depends on this, I may know only 30%. 30%, 1 minus PC is 30%. Then 30% is enough to identify. So limited knowledge, for example, if you go to a supermarket, for example, and take 10 people and find out from them by a questionnaire who is the one that meets with many more people and immunize him or quarantine him, then you need much less units of immunization, much less people to quarantine. And you see it here for different type of networks. it increases very fast to the case where when you have all the knowledge. These are different networks, you have very different networks. It means after 10 people, you almost have almost the knowledge of the whole network. So it means that limited knowledge is not really limited. If you have enough people, 10 people, you can get the results almost as you know everything in the network. And we tested this also on many real networks. And we see here also that, of course, if you know only one, you need to immunize almost everyone. You need 100%. But when you know 10 people, you need to immunize only 20%. It means that very few people is like knowing a lot about information. And this is very important for the current epidemics, current pandemic. Imagine that we don't have enough immunization units, so we can make this system, and instead of needing to need 20%, like here, you can need only 20, I'm sorry, instead of needing 75%, the difference between here and here, you will need only 20%. So you can reduce the number of units to immunize the people by partial limited knowledge. So let me summarize. I think we are almost 10, 20 minutes. So what I showed you, that we can distinguish between fake and real news based on network structure. No text, without text, you can distinguish 76% of the network after 5 hours. What I showed you also is the pandemic, spatio-temporal spreading, and how efficient immunization. We compared China to Italy. We can see very strong difference between China. China, the spreading decayed very fast in time scales of 10 days, while here it's 50 days, but 50 days is almost like all the time. Now we can do also other spreading. I just mentioned here, cascading failure spreading in infrastructures. This is this paper. Spreading of traffic jams, how traffic jams are spread, because jam in city start in a place and then it spreads. So this is a very nice paper that shows universal size distribution of it appears the same spreading phenomena appears everywhere in many cities. Also spreading of failures in financial market, you can look on this paper. And we can, by this way, ranking economic in countries, which economic is more stable than others. And for example, we can see in this figure that China, for example, was lower than USA and Germany before 2002, but it becomes stronger after 2002 and stronger in their economy. And we can see the transition very nice using by spreading of failures. We assume a failure in the financial system and we see how it spreads and how it breaks the system. And last, I want just to mention one more work that we are now, I hope soon be published, is spreading of human flow in cities. And this is a nice picture of Tokyo area. And you can see how the spread in rush hour occurs. You can see that all the same color, they are all following in the same direction. All the blue, they all follow in one direction, another direction. And we measured it in many cities in China, and we see that in the morning rush hour, this is what you see, flow, clusters of flow, and the universality is the distribution of size of the basin size. These are basin size that people go to places. You see here is Tokyo, and you can see universality. Hopefully in a few weeks, this will be published. Thank you very much for your attention.